This will be a review of stoichiometry, which is the relationship between amounts of reactants and products in a chemical reaction. So using stoichiometry, we can determine how much of a reactant we need to form a certain amount of product, or how much we need to react completely with another reactant. So let's think about what information we can get from a balanced chemical equation, because that's kind of the root of stoichiometry problems. So in this example, we have sulfur trioxide reacting with water to form sulfuric acid. And in the equation, there are no stoichiometric coefficients, which indicates that all of the stoichiometric coefficients are 1. So what does this tell us? How can we interpret this reaction? So one way that we could interpret it is if we have 1 mole of sulfur trioxide reacting, 1 mole of water will react, and 1 mole of sulfuric acid will form. We could also interpret this in terms of masses. So if we calculate the molar mass of each of these, the molar mass of sulfur trioxide is 80.06. So 1 mole would be 80.06 grams. So if 80.06 grams reacts, that means that 18.02 grams of water reacts, which is the molar mass of water, so the mass of 1 mole of water, and 98.08 grams of sulfuric acid will form, which is the molar mass of sulfuric acid. So one other way that we can interpret this is that 1 molecule of sulfur trioxide reacts with 1 molecule of water to form 1 molecule of sulfuric acid. So the balanced chemical equation tells us how many moles of reactant react with another molecule or reactant to form some quantity of products. So in this case, everything's 1-to-1, so we need 1 mole of each reactant to give 1 mole of product. So let's look at a slightly more complicated example where we don't have everything reacting 1-to-1. So in this case, we have iron oxide reacting with sulfuric acid. And so in this case, the stoichiometric ratio tells us that 3 moles of sulfuric acid react with every 1 mole of iron 3 oxide. And so using the balanced equation, we can answer a lot of different kinds of questions. So in general, the steps that we want to use when solving a stoichiometry problem: first, we want to make sure we have a balanced chemical equation, because all of the calculations will be off if the reaction isn't balanced properly. And we use this to determine stoichiometric ratios. And then if you're given a mass or volume of reactant, you always want to convert that to a number of moles. And you do this either using molar mass if you have a mass of compound, or concentration if you're given a volume. This is key. You can't ever convert between masses of reactants and products, or or volumes of reactants or products. So you always want to get from mass or volume to number of moles. Once everything's in moles, we can use the stoichiometric ratio to calculate the amount of the other reactant or product that has to react or form. And then we can convert back from number of moles to either mass or volume, depending on what the problem's actually asking. So if we look at this reaction of iron oxide with sulfuric acid, we're asked what volume of 0.5 molar sulfuric acid is required to react completely with 5 grams of the iron oxide. So the first step is always to make sure we have a balanced equation, which I already told you that it's balanced. But you should check that for yourself. And then the next step is to convert the mass of iron oxide to moles. So to do that, we need the molar mass of the iron oxide. And so we can calculate that based on the formula of the iron oxide and the molar masses of each of the atoms in it. So from the formula, the subscript of 2 indicates that we have 2 iron atoms. So we're going to multiply 2 by the molar mass of iron. And then from the formula, we see that for every 1 formula unit or molecule, we have 3 moles of oxygen. So we'll multiply 3 times the molar mass of oxygen. And that comes out to 159.7 grams per mole. So now we take the initial mass of iron oxide, and we want to convert to moles, so that means we need to divide by grams. And multiply by moles, so we're just dividing by the molar mass. So that means that we are starting with 0.031 moles of iron 3 oxide. And so now the next step is to use the stoichiometric ratio to determine the number of moles of sulfuric acid needed to react with all of the iron oxide. So we know that all 0.031 moles of iron oxide will react. And now from the balanced equation, we know that 1 mole of iron 3 oxide reacts with 3 moles of sulfuric acid. And we know that we want to be dividing by moles of the iron oxide because we want that to cancel out. And so that comes out to 0.093 moles of sulfuric acid. So now the last step is to get back from moles, in this case, to volume. And in this case, we can use concentration. So we're told that we have a 0.5 molar solution of sulfuric acid. So that means we have 0.5 moles of sulfuric acid in 1 liter of solution. And so we again start with our 0.093 moles of sulfuric acid. And we want to divide by the molarity because we want moles to cancel out. And so that comes out to 0.19 moles of sulfuric acid. And now the only thing that we have to stop and think about is whether or not we're using the correct number of sig figs. So if you recall, when you're doing multiplication or division, you keep the lowest number of sig figs. So in this case, we're given 0.5 molar H2SO4 and 5 grams of the iron oxide. Both of those values have 2 sig figs, so that means that our answer should have 2 sig figs. So that means that our answer is fine. So in the previous example, part of the example, we calculated what volume of reactant we needed to react with all of the iron oxide. Something else that we can do is calculate how much product should form if all of the iron oxide reacts. So in this case, the first two steps are the same as the first example. We already know we have a balanced equation. And from the first example, we know how many moles of iron oxide we have. So we're starting still with 0.031 moles of iron oxide. So the first two steps are the same as part A. So now, starting with that amount of iron oxide, our step 3 will be to convert to moles of iron sulfate with the stoichiometric ratio. So again, we're starting with 0.031 moles of iron oxide. And now, from the balanced equation, we know that for every 1 mole of iron oxide, we form 1 mole of iron sulfate. And we could have predicted this just by looking at the balanced equation, because we see that the stoichiometric coefficients for the iron oxide and the iron sulfate are the same. So now that we have moles of iron sulfate, we need to convert them to grams. And so from that, we would need to calculate the mass of the iron sulfate. So the molar mass of the iron sulfate. So again, we have 2 iron molecules for every 1 iron sulfate formula unit. And then we also have sulfur and oxygen present. So each sulfate ion in the formula unit contains 1 sulfur, but we have 3 sulfate ions. So that means we have 3 sulfurs. And then each sulfate anion has 4 oxygens, and we have 3 sulfate ions. So that means we have 12 oxygen atoms. So we need to multiply that by the molar mass of oxygen. And that gives us our molar mass of the iron sulfate. And so now it's just a simple conversion from moles to grams. Again, where we're going to divide by the molar mass. We need to multiply by the molar mass because we want to convert from moles to grams. So we want the 1 mole to cancel. And so that comes out to 12 grams of iron sulfate. And again, we want to have 2 sig figs because we had 2 sig figs in that original value. So to summarize everything that we've just done, we found that we need 0.19 liters of sulfuric acid to react with 5 grams of iron oxide. And that forms 12 grams of iron sulfate. So we can summarize all of this in what we call a reaction table or an amounts table. So in the table, we're going to start by writing the balanced equation. And so we'll fill in initial amounts in moles. So we know that we start out with 0.31 moles of the iron oxide and 0.093 moles of the sulfuric acid. And initially we don't have any products. Then we calculate a change. So we know that we've calculated it such that all of the reactants are consumed. So the iron oxide decreases by 0.031 and the sulfuric acid by 0.093. And then we know that 0.031 moles of iron sulfate will form. And then we can fill in the water, even though the question didn't actually ask it. And this is actually a pretty simple calculation because we can see that for every 3 moles of sulfuric acid that react, we form 3 moles of water. So that means the same number of moles of water form as sulfuric acid react. And so our final amounts will be 0 for each of the reactants, and then 0.093 and 0.031 for the products. So in this example, we were in a situation where we had a certain amount of reactant and we wanted to calculate how much of the other reactant we needed so they both were consumed completely. It's very common for reactions to be carried out where one reactant is in excess, and the reason for this is to make sure that one of the reactants reacts completely. So if one reactant is in excess, the other reactant will be completely consumed in the reaction, and it's referred to as the limiting reactant. So in these cases, some of one of the reactants is going to remain at the end of the reaction. So what this means is that in stoichiometry calculations that involve a limiting reactant, the first thing you need to do is figure out which one it is, because it's the limiting reactant amount that's going to need to be used to calculate how much of the other reactant is consumed and also how much products form. So ammonia and oxygen react to form nitrogen monoxide and water. So we have a sealed vessel where we have 15 grams of each of the reactants. And so we want to know 2 things. We want to know which reactant is limiting and what mass remains when the reaction is complete. So what mass of reactant in excess remains, and then also how much product, in this case water, is formed in the reaction. So the first thing that we need to do is write a balanced chemical equation in order to do both parts of these problems. So we're given the formula for ammonia. Oxygen gas is diatomic, so it's going to be O2. Nitrogen monoxide is just NO, and then water. So you should review naming molecules and naming ions as well. So the previous example had some ions in it. So the first thing we need to do is balance the reaction. So if we look at this, we see that nitrogen is balanced. We have one on each side of the reaction. We have 2 oxygen in reactants and 2 oxygens in the products. So it's just the hydrogens that we need to balance. So we have 3 hydrogens in the reactants and 2 in the products. So if we place a coefficient of 2 in front of the ammonia and 3 in front of the hydrogen, we now have our hydrogens balanced. The only problem now is that our nitrogen and oxygen are no longer balanced, so now we need to go back and balance those. So we see that we have 2 nitrogens in the reactants and 1 in the products. So if we multiply by 2, we'll balance the nitrogens. And so now we just have to balance the oxygen. So we have 2 in the reactants and we have 2 plus 3, so 5 in the products. So the easiest way of dealing with this is to first multiply the oxygen by 5 halves, because that'll give us a total of 5 oxygen atoms. And then we want all whole number coefficients in the balanced reaction, so we're going to multiply the entire thing by 2. So our balanced equation is 4 ammonia plus 5 oxygen to give 4 NO plus 6 water. So now that we have the balanced equation, this can tell us something about the required stoichiometric ratio. So we know that we're starting out with 15 grams of ammonia and oxygen, but we don't know how much that is in moles yet. So the first thing that we want to do is evaluate how many moles of oxygen do we need to react with X number of moles of ammonia. So from the equation, we know that we need 5 moles of oxygen for every 4 moles of ammonia. And so that reduces to 1.25 moles of oxygen for every 1 mole of ammonia. So this is our required stoichiometric ratio. And so we need to use this in order to determine what the limiting reactant is. So that brings us to step 2. So that is to convert masses of reactants to moles of reactants. So we're starting out with 15 grams of ammonia. We need to divide by the molar mass to find moles. So we have 0.8808 moles of ammonia. And we're also starting with 15 grams of oxygen. And so we divide by the molar mass of oxygen. To get moles of oxygen. So now we want to determine the mole ratio of oxygen and ammonia that's present and compare that to what is actually required. So dividing the moles of oxygen by moles of ammonia tells us that we have 0.53 moles of oxygen for every 1 mole of ammonia. And so that's less than the 1.25 that's required. So what this means is that we don't have enough oxygen present to react with all of the ammonia, and so the oxygen is the limiting reactant. So the important part here is that now that we know that oxygen is the limiting reactant, when we do the rest of our calculations, we need to use the number of moles of oxygen in them. If we use moles of ammonia, we won't get the right answer because we have more ammonia present than we can react with all of the oxygen. So there will be ammonia left over, and so we have to base our calculations on oxygen. So if we come back to part A, so we determine the limiting reactant, and now we want to know how much ammonia remains when the reaction is complete. And so we'll use the number of moles of oxygen that reacts to find the number of moles of ammonia that react. So we know that 0.4688 moles of oxygen react. And from the balanced equation, we know that 5 moles of oxygen react with 4 moles of ammonia. And then I'll continue it in one calculation. So that will give us moles of ammonia, but we want to know grams. So if we have 1 mole of ammonia, the molar mass is 17.03. So now that we know the mass of ammonia that reacted, we can calculate the mass of ammonia that remains. And it's just going to be the mass of NH3 initially minus the mass that reacted. And then we want to pay attention to sig figs. So we had 3 sig figs in our initial mass, and so that means that our answer can have 3 sig figs. So the last piece is part B, which is what mass of water forms in the reaction. So when we calculate the mass of water that forms, we need to again make sure we start with the moles of oxygen to calculate the moles of water, and then the mass of water. And again, the reason that we have to do this and make sure that we use oxygen is that the oxygen is the limiting reactant. So only all of the oxygen will be consumed. If we use the number of moles of ammonia, we would get a mass of water that can actually be formed because we don't have enough oxygen. So I'll start by rewriting the balanced equation. And so now we start with moles of oxygen. And now from the balanced equation, we know we want to cancel moles of oxygen, so we're going to divide by 5 moles of oxygen. So from the balanced equation, we know that for every 5 moles that react, we form 6 moles of water. So we multiply by 6 moles of water. And then we want to convert to mass, so we want to use the molar mass of water. And so we multiply by that. So that comes out to 10.1 grams of water. And again, sig figs are correct because we have 15.0 grams of each of the reactants, and so we can have 3 sig figs in our answer. So there are additional practice problems on stoichiometry posted on Sakai. I recommend that you review them and practice them, and if you have any issues with concepts, come back to these slides and use them to guide you in making sure that you understand stoichiometry.